How do you intuitively understand displacement current in E? Imagine you're watching a water hose. When you turn on the tap, water flows out, creating a current. Now picture a situation where the water isn't flowing but the pressure changes. That's similar to what displacement current is in electrical engineering. It's not actual charge moving through a wire, but a way to describe how changing electric fields can produce magnetic effects. In a typical circuit, conduction current is the flow of electrons through a conductor, which creates a magnetic field around it. But what happens when you have a capacitor? The two plates are separated by an insulating material called a dielectric, so no charges actually move across the gap. Still, when you charge or discharge the capacitor, the electric field between the plates changes over time. This changing electric field can generate a magnetic field just like a real current would. To understand this better, think of the electric field as a kind of invisible force that can change in strength. When it changes, it creates a kind of virtual current called displacement current. It's like a way to keep the idea of current flowing, even when no charges are physically moving. The key is that the electric displacement field, which depends on the electric field and the medium's permittivity, changes with time. This change is what we call the displacement current. Mathematically, it's expressed as the rate of change of the electric displacement field over time. The electric displacement field relates to the electric field and the permittivity of the material, which tells us how much electric field a material can store. When the electric field varies, the derivative of the electric displacement with respect to time is not zero, and that's the displacement current density. This concept was introduced by James Clerk Maxwell to make sure the equations describing electricity and magnetism stayed consistent. He modified Ampere's law to include both conduction current and displacement current. This change allowed the equations to work even in regions where no actual charges move, like inside a capacitor during charging. In practical terms, displacement current explains why alternating current signals can pass through capacitors in circuits. It is essential for understanding how electromagnetic waves travel, how antennas work, and how high-frequency circuits behave. It bridges the gap between static electric fields and dynamic electromagnetic fields, making it possible to analyze and design devices that rely on changing electric and magnetic fields. So, intuitively, displacement current is like a shadow or a mirror of changing electric fields. It's not real charge moving, but it acts as if it is, producing magnetic effects. This idea helps engineers treat regions without physical charge flow as if they carry current, keeping the laws of electromagnetism consistent and allowing us to predict how fields behave in real-world applications.